Hello everyone, and welcome to some more remote learning. Today we're going to be going over vectors. So this is our first introduction into more than 2 dimensions. We're going to be working in 3 dimensions. However, for this worksheet, even though we're going to be working in 3 dimensions, we're going to still be working in a plane. And that plane that we're going to be working in is the XY plane. So let's go ahead and dive into this vector overview. Now, many of you have seen vectors before in physics, in statics, so this is a bit of a summary, and if it's new to you, hopefully more of an explanation. So a vector is a quantity that has length, otherwise known as the magnitude, and direction. So really, let's understand PQ and its vector notation, so vector PQ. The way a vector is set up is that if we have some point P and some point Q, in order to create vector PQ, P is known as the tail and Q is known as that head. So we're going to start at the tail and draw the arrow to the head. And there we have it. There's our vector PQ, P being the tail, going to the head, Q. Now let's just pick a point. Let's say that P is the point 0, 0, and we'll make Q the point 3, 4. Now in order to make vector PQ, we do head minus tail. That's how we form that vector. So vector PQ will be the head, that x value of the head, so 3 minus the x value of the tail, 0, comma, the y value of the head minus the y value of the tail. So vector PQ is 3 minus 0, which is 3, comma, 4 minus 0, which is 4. So PQ is the vector 3, 4. So you can see that it has direction, the individual components of the vector, as the first one, the x component, and the second one, that y component. Or, eventually we'll get into an I component and a j component. So again, one more time to form that vector given 2 points, it's head minus tail to get our vector. So we can see easily the direction of this vector, but what is its length? What's its magnitude? Well, that's a formula, and the formula is going to be the magnitude of some vector v is going to be equal to each of the vector components squared, summed together, and the square root of that sum. So the square root of v1 squared plus v2 squared. So if we're dealing with vector PQ, the magnitude of vector PQ is going to be the square root of 3 squared plus 4 squared. So you can see there's my first component and my second component of the vector. So that's going to be the square root of 9 plus 16, which is the square root of 25. So 5 is the length of that vector. And just so you can understand where this formula comes from, think about this. If I formed a right triangle, having PQ be the hypotenuse of my triangle, then the length in the x direction is 3, and the length in that y direction is 4. So obviously this isn't quite drawn to scale, but if this was a length of 3 and this was a length of 4, how do you find the length of the hypotenuse? That's the square root of my sides squared. So that's just the Pythagorean theorem. A squared plus b squared, the square root of that. And that's all to find the length of that vector, which we got was 5. So now we understand that a vector has both direction, which is made by its components, and magnitude, which is that length. Now there's a very specific vector which will be helpful not only in this lesson, but later lessons. For now though, a unit vector is exactly what it sounds like. Unit, a length of 1. So a unit vector is a vector that has a length of 1. So if we have some vector v that has some length, we don't know what that length is, if we divide by the length or by its magnitude, that becomes a unit vector. So if we take our vector PQ, which was 3, 4, and if we divide that by the magnitude of PQ, which we got to be 5, then we have 3/5, 4/5. This is a unit vector, and you can see that if we took the magnitude of our unit vector, we will indeed get 1. So just to show you, let's take the square root of 3/5 squared plus 4/5 squared. We'll get the square root of 3 squared is 9 over 5 squared is 25 plus 4 squared is 16 over 5 squared, which is 25. This becomes the square root of 25 over 25, which is the square root of 1, which does indeed equal 1. So in order to create a unit vector, all you have to do is take the vector and divide it by its own magnitude. That will give you a unit vector. And that unit vector will point in the same direction as the original vector. So I could easily ask for a unit vector in the opposite direction. And then if I wanted something in the opposite direction, all I'd have to do is multiply by a -1. And we'll get into that when we talk about scalars. So now that we understand exactly what a vector is, that it has direction and magnitude, in order for two vectors to be equal, they have to have that same exact magnitude and the same direction. So, for example, let me give you two other points. Let's do R and point S. R will be the point 1, 2, and S will be the point 4, 6. Now, if I want to find vector RS, remember, all I have to do is head minus tail. That's going to be 4, the x-coordinate for S, minus 1, the x-coordinate for R. Remember, head minus tail. That's going to be my first component of vector RS, and then I need to do 6, that y-coordinate from S minus my y-coordinate from R, which is 2. So if I did this, RS, 4 minus 1 would be 3, 6 minus 2 would be 4. RS is equivalent to that above vector PQ, because remember, PQ was vector 3, 4, and RS is also vector 3, 4. Same direction, and they also happen to be the same exact, so that's going to give us the same magnitude. So just because I'm not necessarily starting at the origin, 0, 0, those vectors are the same. Now, going back to a scalar is just a quantity with magnitude and no direction. So you can think of a scalar as a real number. And a scalar can be multiplied to my vectors and then just distributed through to each of those components. So up above, when we were talking about the unit vector, for PQ, we had 3/5 and 4/5. That was the unit vector in the same direction as vector V. If I wanted something in the opposite direction, I would just multiply this whole thing by a scalar of -1. Doing that would give me the vector -3/5 and -4/5. So the opposite direction of vector PQ, but still a unit vector. So let's go ahead and draw a couple of those vectors out. So if I put my original vector PQ, and we know that has a length of 5. My unit vector has a length of 1, and it points in that same direction. So I'm just going to draw it next to it with a length of 1 pointing in that same direction. Now we just calculated a vector pointing in the opposite direction, but remember, vectors tell me magnitude and direction. It doesn't matter where I'm starting them from. So I'll do my vector pointing in the opposite direction here. So there's my unit vector of PQ pointing in the opposite direction that PQ goes. I could also simply scale my unit vectors by multiplying them to make a vector of any length I want in that direction of PQ. So for example, if I took that 3/5 and 4/5, and let's say as opposed to having a length of 1, I wanted this vector to have a length of 2, all I would need to do is multiply that unit vector by 2 to create a vector of length 2. So that would be 6/5 and 2 times 4, 8 over 5, 8/5. So if you can envision this one, I'll start this vector here with a length of 2. There we have it. And obviously these aren't perfectly to scale, but roughly they're there. Now what do you notice about all the vectors that I've drawn? Well, they're either pointing in the same direction or the opposite direction, but notice that they're all parallel to one another. And that's because two vectors are parallel if they are scalar multiples of each other. And how I created all of these vectors was just by multiplying by some real number. So in order to tell if two vectors are parallel, you just have to see if they're scalar multiples of one another. AKA, can you take one number and multiply or divide the vector by it to get that other vector that you have? And the last note before we really jump into examples is that the 0 vector, 0, 0, has a length of 0 and no direction. So because it has a length of 0 and no direction, it's still going to be defined as a vector, but because it has no direction, it's going to be parallel to all other vectors. Lots of times a 0 vector is noted as a 0 in vector notation. That just represents the 0 vector. So if we're working in a plane, that would be 0, 0. If we're working in 3 dimensions, that would be 0 in the x, 0 in the y, and 0 in the z, which we'll jump into in the next example video. But for now, we're just working with that xy plane. So for example 1, using this figure below, we're going to write the following vectors in terms of vector u or in terms of vector v. So looking at that first vector, we're trying to figure out vector rp. Remember, tail to head, r to p, is this vector here, which, well, what does that vector look like? It's vector u, just starting at a different point. So rp is vector u. Those are equivalent vectors. So in part B, as opposed to doing rp, the head and tail are switched. We're now going from p to r. So r is now the head of our vector. So if I was to redraw this, I would start at p, drawing to r. And this is just vector u, but in that opposite direction. So we're just scaling it by a -1, multiplying it by a -1 to get that opposite direction. So vector PR is equivalent to negative, or the opposite, of vector u. Now let's look at our next vector, QR. So Q to R, you can see that that's similar to vector V, except we're going in that opposite direction. So this is the opposite of vector V, whereas R to Q is going in that same direction as V. So I'm just shifting my starting point of my vector V. So RQ is equivalent to vector V. It has the same length, which is easy to see here because we're just going in that x direction. Vector V has a length of 2, vector QR has a length of 2, and they're both going in the same direction. So RQ is equivalent to V. Now, another way we can handle vectors is by adding or subtracting them, just like we can real numbers. Except remember, vectors are broken up into their different components. So in order to add vectors together, we're going to add their components together. So if I have vector u, and that's going to be u1, comma u2, if I'm adding that to vector v, which I'll write as v1, comma v2, then, just like I said, I'm going to be adding those similar components together, and that will give me a third vector. So I'll do my first component, u1 plus v1, comma, my second components added together, u2 plus v2. And that will give me a vector. Adding two vectors together results in a vector. Same with subtraction. If I have u1, u2, and I'm subtracting some vector v1, v2, that's going to be equivalent to u1 minus v1, comma, u2 minus v2. And again, the addition or subtraction of vectors forms a new vector. So getting into example 2, again, we're going to refer to that figure above, but we're going to write the following vectors as sums of scalar multiples of u and v. So for a, b, and c, we're going to do a little bit of scaling and summing of vectors. So our first one we're looking at is qp. So let's go back up and draw the vector qp. Remember, tail to head, q to p. You can see that this is not simply u and it's not simply v, but it is the combination of u and v. If we take vector u, which goes this way, if we added vector v, we would get to this point here. So as opposed to taking this vector v and adding it to u, I want to, as opposed to adding it, I want to scale vector v. I want to go to the right in that opposite direction. So I'm going to take vector u and subtract vector v. That will get me from q to point p. Vector qp would be u minus vector v. And remember, if you want to think of this as addition as opposed to u minus v, it's like vector u plus a negative vector v. Addition's commutative, so we can also move the other way. Let's move first a negative v, which would give us that vector qr, but then to that add u. You can see that again, we still result in that qp vector. So vector u minus vector v, or the opposite of vector v plus vector u. So again, this is vector u minus vector v. Now let's look at our next vector, qo. So qo is going to be equivalent to, if I'm starting at point q and drawing my vector to o, there we have qo. Using just vectors u and v, how do I go from point q to point o? Well, because this is based off the origin, you can already see if I added vector u, I'd get to this point here. If I added another vector u, so if I did 2u, I would have this vector here. And if I have 2u now, all I have to do is add vector v. Because once I add vector v to 2u, you'll see that I'll go from q to o. Vector qo. So that's 2u plus v. And again, addition's commutative, so I could have started by adding vector v and then going to u. So qo is 2 times vector u, so scaling vector u by a quantity of 2, plus 1 of vector v. Next, we're going to do vector po. So I switched this up here because we're no longer starting at that origin, which is easy to see where our vectors are going from. So p to o. Well, how do we want to start this? It's easy to see that po is not simply vector u and it's not simply vector v. It's going to be some combination of those. So if I started with vector u, going 2 over and 2 up, I would be here. And then, now you can see I have 1, 2, 3, 4 spaces in that x, and v was a length of 2, so now I need to add 2v. So 2 times vector v plus 1 of vector u will go from point P to point O. So u plus 2v. Now, an alternative way to writing vectors is to write them as multiples or scalars of a coordinate unit vector. And a coordinate unit vector is vector I is 1, 0, so that x direction taken into account, and vector j is that y direction taken into account, 0, 1. And if we were in 3 dimensions, we'd have some vector k, 0, 0, 1. So in that z direction, which we'll get into in a later example video. So given our coordinate unit vectors, we're going to use the above figure again, but this time we're going to plot those coordinate unit vectors, and we're going to write the following vectors in the form of a times vector I plus b times vector j. So let's go ahead and start by plotting those coordinate unit vectors. So remember, I is vector 1, 0, and I'll base these off the origin. Although, remember, I could draw 1, 0 up here, and that's still the same as drawing it down here. The starting point of that vector does not matter, it's just the magnitude and direction that does. But just to make this easier, let's base it off that origin. Here is vector I, and here is vector j. And note that each of these are unit vectors. Each has a length of 1. So the second part of that question said that we're going to write the following vectors in the form of a times vector I plus b times vector j. So as opposed to writing it as some scalar of u plus some scalar of v, we're going to use our I and j vectors. So QR is the first one we're going to figure out. QR is this vector here, which we can see as not 1i, but 2 of vector I. So QR will be 2i plus 0j, or simply 2i. Next, we're going to look at vector QP. So looking at vector QP, that's starting at Q and going to P, well, you can see that we're going 1, 2, 3, 4 I and 1, 2 j. So 4i, 2j. And again, I'm just scaling those vectors and adding them together. Lastly, we're going to do vector OQ. Starting our vector tail O to head Q. So that would be minus 2i, so taking I and multiplying it by a negative 2, and then 1, 2, 3, 4, taking j and multiplying it by a negative 4. So vector OQ is going to be negative 2i, so here's negative I and then negative 2i, plus negative 4j, negative 1, negative 2, negative 3, negative 4, to form vector OQ. Or I can write this as negative 2i minus 4j, just as long as that b is negative. And just a quick note, remember that vector OQ points in the opposite direction of QO. So if it was easier to envision vector QO as a positive 2i and then a positive 4j, all you would need to do to get that opposite direction is multiply by a negative 1. So that would give you a negative 2i and a negative 4j. And really quickly, if you think about it, when we're scaling I, we're only changing that x component of our vector, because multiplying a scalar to 0 is still 0. And when we're multiplying some scalar to j, we're only changing that y component of the vector, because multiplying anything to that first component of 0 will still be 0. So 2i plus 0j, I can write that as vector 2, 0. Or 4i plus 2j, I could write that as 4, 2. Or negative 2i minus 4j, I could write that as negative 2, negative 4. So again, this was just an alternative form to expressing a vector. Let's jump into example 5. In example 5, we're going to be finding the magnitude and dealing with unit vectors. It says given points P, negative 2, 1, and R, 2, 6, we're going to find vector PR. Remember, that's going to be head minus tail. So vector PR is going to be 2 minus a negative 2, the x-coordinate of R minus that x-coordinate in P, comma, the y-coordinate minus the y-coordinate, 6 minus 1. So this is going to be 2 minus a negative 2 is 4, and 6 minus 1 is 5. So vector 4, 5. Now we're going to express PR in the form from above. So A is going to be 4 times that vector I plus B is going to be 5 times that vector J. So again, I'm taking that X component and multiplying it by vector I and that Y component and multiplying it by vector J. Next, we're going to find the length of vector PR. And remember, length is just another word for the magnitude of that vector. So calculating the magnitude of PR, we're going to take each of the components, square them, sum them together, and then take the square root of that quantity. So we'll do the square root of 4 squared plus 5 squared, which is equal to the square root of 4 squared is 16 plus 5 squared is 25, which is the square root of 41. And the square root of 41 cannot be simplified. So the length of vector PR is the square root of 41, which is about 6.4. But we'll just leave it as the square root to keep it exact. So in our next part, we're going to find the unit vector with the same direction as PR. So remember, that same direction, just make it a unit vector. So we're going to take vector PR and divide it by its own magnitude. That will give us a vector in the same direction as PR that has a length of 1. So we'll take 4, 5 and divide it by the square root of 41. Now you can leave it as this, or you can write it as 1 over the square root of 41 out in front of our vector 4, 5, or feel free to distribute it in. So that's going to be 4 over the square root of 41, comma, 5 over the square root of 41. That's a unit vector in that same direction as PR. Our last part says to find two vectors parallel to PR with a length of 3. Now the easiest way to create a vector of a certain length is to take the unit vector and multiply it by the length you want. And remember, multiplying a vector by a scalar is going to create a parallel vector. So if we want a vector that's parallel to PR with a length of 3, all we have to do is multiply the unit vector by 3. So we'll do 3 times 4 over the square root of 41 and 5 over the square root of 41, which, if we wanted to write that out, that would be 12 over the square root of 41 and 15 over that square root of 41. So that's one vector that's parallel with a length of 3. We still want that same length of 3, and we also want it to be parallel, so what else can we do? Well, vectors that point in the opposite direction are still considered parallel. So as opposed to multiplying the unit vector by positive 3, let's multiply it by negative 3, because it still is going to be a length of 3. It's just going to be pointing in that opposite direction. So another vector will be negative 12 over the square root of 41 and negative 15 over the square root of 41. So essentially, I just multiplied negative 1 to the vector that I already created with a length of 3. And just to get you thinking about this, when we multiply by a positive scalar, we're going to wind up going in that same direction as our original vector. Whereas if we multiply by a negative scalar, so if some scalar is less than 0 and we multiply it to our vector, we wind up pointing in the opposite direction as our original vector. They are all still parallel. So for our last example on this example worksheet, we're just going to actually apply what we learned about vectors. So for this example, it says that the water in a river moves south at 2 miles per hour, and a motorboat travels due east at a speed of 10 miles per hour relative to the shore. So if we pick this problem apart, if we're moving south, I'll do north as a positive y, south as a negative y, east as a positive x, and west as a negative x. Drawing this, if a motorboat is traveling due east at a speed of 10 miles per hour, that's a vector moving in the x direction, and that vector is 10 miles per hour. So essentially the magnitude or length of that vector is 10. And that's relative to the shore. So if our current was moving 2 miles per hour south, if we were standing on the shore and the boat looked like it was traveling due east, that means that the boat had to be attempting to fight that current a little bit. So if I drew my vector 2 miles per hour here, then I know logically that the boat would have had to be traveling with a slightly north heading. So some vector here is what we're trying to figure out. We're determining the speed and we're going to determine that direction. So the speed, let's start with that because the speed is essentially the magnitude of our vector. So if we want to think of this 10 mile per hour vector as 10 in the x and 0 in the y, and this 2 mile per hour vector as 0 in the x and negative 2 in the y, then how would we create that green vector, the way the boat had to move relative to the water? Well, that's our vector 10, 0 minus our vector 0, negative 2. So that vector is going to be vector 10, 2, because the velocity relative to the shore, which is at 10 miles per hour, is our speed and direction relative to the water, plus that speed and direction of the water. That gives us our speed and direction relative to the shore. So relative to the shore minus our water would give us relative to the water. So again, speed's just the magnitude of that vector. So the magnitude of 10, 2 is going to be the square root of 10 squared plus 2 squared, which is the square root of 100 plus 4, the square root of 104, which we can simplify this square root down. Because 4 is a factor of 104, the square root of 104 is the square root of 4 times 26, which is 2 root 26, because we cannot simplify the square root of 26 anymore. So our speed is 2 square root 26 miles per hour, which is about 10.2 miles per hour when written as a decimal, which makes sense for our problem. Now we have to determine that direction of the boat. And the direction we'll want to write as some degrees, north, south, east, west, some combination of that. So what we have to do is figure out some angle so we know what direction that boat headed. So the angle I'm going to solve for is this angle theta here. And that angle theta will tell me the direction the boat headed north of east. And I'll just use trig functions to figure this out, because the length of my vector is that velocity. So this vector had a length of 2, this vector had a length of 10. So I can do the tangent, because tangent is opposite over adjacent. I will do the tangent of theta equal to 2 over 10, which means that I just have to take the inverse tangent of 2 over 10 to get my angle. And the inverse tangent of 2 over 10, when entered into a calculator, is approximately 11.3 degrees. So I need to head 11.3 degrees north of east. And this problem worked out very nicely because my given vectors only had one component in each. I was only traveling the x direction and the y direction in each of those vectors. Therefore, my vectors formed that right angle and were perpendicular to one another to allow me to use that inverse tangent function right away. If that wasn't the case, I would have to do some adjusting to form a right triangle in order to find that direction I wanted to head. But again, the speed and direction of the boat relative to the water is 2 root 26 miles per hour with a direction of 11.3 degrees north of east. And that wraps up our vectors in the plain worksheet. If you have any questions, leave them in the comments below. And in the next example video, we'll start jumping into those 3 dimensions, so using a z component with our vectors. So until next time, good luck with your studies.